Gravity is the force that holds the universe together. Like the galaxy in which we live, it seems to be eternal and unchanging. However, our current understanding of gravity paints a rather different story. Gravity can bend and twist the shape of space itself, and, if that's true, then it's very interesting to ask how quickly those distortions can move. In its simplest form, the question is, how fast is gravity? Let's look into it. The speed of gravity is a question that has puzzled scientists for centuries. The first sophisticated theory of gravity was developed by Sir Isaac Newton and first published way back in 1687. According to Newton, gravity was transmitted everywhere across the universe at infinite speed. However, Newton's theory of gravity isn't the newest and most successful theory of gravity. In 1915, Albert Einstein published his theory of general relativity, which interprets gravity as the distortion of both space and time. In his theory, these distortions could change the shape of things like stars and planets, and, of course, space itself. These changing distortions would then move through the cosmos by means of a phenomenon called gravitational radiation. He postulated that the speed of gravitational waves was identical to the speed of light. Thus, Einstein would say that the speed of light and the speed of gravity are the same. So who's right? Well, Einstein and Newton are both strong contenders in any contest for the title of most influential physicist of all time. I mean, I would pay good money to watch those two guys debate, but when you get right down to it, it doesn't much matter what either of them think. Physics is an empirical science, and answering the question requires a measurement. So how would you measure the speed of gravity? Well, first and foremost, you need to be able to detect gravitational waves, and that's hard. Gravitational waves distort the size of objects. For instance, if gravitational waves passed over you, they would change your height and width. Your height would shrink and width increase, and then the opposite, with height increasing and width shrinking. And that cycle would happen a few times as the gravitational wave passed over you. That's the basic idea, but do they exist? Einstein predicted they existed way back in 1916, but it took basically a century for scientists to both devise a credible methodology and then develop the technology to do it. Well, gravitational waves are made when any massive object moves. Most waves are ridiculously tiny. The only known way to get big gravitational waves is to rapidly move objects with both tiny volumes and the mass of stars in an oscillating way. It just sounds crazy hard. However, nature is way ahead of us. The universe is full of stars, and many star systems consist of not one star like our solar system, but rather two. And of course, some of these star systems were formed early in the universe, long before our own star formed some 4.5 billion years ago. So these super old stars have lived and died, and some of them are now black holes, which are just long dead massive stars. And in binary star systems, there could be two black holes orbiting one another. The lightest black holes have the mass of 3 times the Sun. Some are much heavier. The smallest known black holes are pretty small, about 6 miles or 10 kilometers in diameter. Those are just ballpark numbers. Because they're heavy and small, two black holes can get very close to one another, and when they orbit, they move at an appreciable fraction of the speed of light and undergo extreme acceleration, and therefore they emit appreciable amounts of gravitational radiation. On the other hand, black holes are very far away from Earth. Even if they emit a lot of gravitational radiation, when that radiation gets to Earth, it only makes tiny distortion of lengths and widths. That means you need a crazy precise detector. So, back in the 1990s, researchers began building what are called the LIGO facilities. LIGO is short for Laser Interferometer Gravitational Wave Observatory. Each facility consists of 2 hollow tubes. Each tube is 4 kilometers or 2.5 miles long. The two tubes are oriented in the shape of an L. A laser is shined down the tube to a mirror and then reflected back to a detector. Using some very precise optics and multiple reflections, the LIGO facility can measure changes in the length of the legs as small as 1/1000th the length of the proton. It's just amazing. I should say that there are actually two LIGO facilities in the US, one in Louisiana and one in Washington State, as well as similar facilities in Europe and Japan. The multiple sites make it possible for scientists to determine where in the sky gravitational waves are coming from. So, it took a long time to get going, but in 2015, researchers made their first observation of gravitational waves, which were made when two rapidly orbiting black holes crashed into another about 1.3 billion light years away. It literally happened a long, long time ago in a galaxy far, far away. So, being able to detect gravitational radiation is super important, but it doesn't tell us how fast gravity actually moves. I mean, you do get some information from when the gravitational waves pass over the various detectors arrayed across the Earth. For instance, the distance between the two American LIGO detectors is 3,000 kilometers, or about 1,900 miles. If gravitational waves wash over the Earth, they'll hit one detector first and then the other. And you can use the time difference to get a handle on the speed of gravity. But the time difference also depends on the orientation of the Earth when gravitational waves pass through the Earth, so it's not so precise. To get a precise measurement of the speed of gravity, ideally you'd like to know exactly when the black holes collided, but since colliding black holes are invisible, that's hard to do. However, again, nature has helped us. While colliding black holes can make gravitational waves, it's not the only way. Remember, what we need is objects with the mass of stars close to one another. Black holes are perfect, but when stars die, not all of them make black holes. Some of them make neutron stars. Neutron stars are less massive than black holes and slightly larger, but they'll still do the trick. If two neutron stars could orbit one another in a very tight orbit and then crash together, that would be great. The collision would both make gravitational waves and a very bright flash that we could see using telescopes. And in the fall of 2017, we got lucky. The Earth's gravitational wave detectors detected the passage of a gravitational wave. And about 2 seconds later, orbiting telescopes detected a brief pulse of gamma radiation coming from deep space. After some analysis, both gravitational wave detectors and telescopes agreed that the source was in the same location in the sky, which was eventually nailed down to being an elliptical galaxy in the constellation Hydra called NGC 4993. NGC 4993 is located about 144 million light years from Earth. Given that we know the speed of light, that means that the collision occurred 144 million years ago. Furthermore, the gravitational radiation and gamma radiation were emitted almost exactly at the same time. From this event in which light and gravitational waves were nearly simultaneously created, we can get very precise handle on the speed of gravity. They both traveled for 144 million years. That's 4.5 times 10 to the 15 seconds. And the two pulses arrived within 2 seconds of one another. And from this, we can say with extremely small uncertainties that gravity moves at the speed of light. The difference is, ballpark, less than 1 part in a quadrillion. Now, you might be wondering why light arrived about 2 seconds after gravity, but the answer is probably simple. Gravitational radiation is emitted all the time, but it's biggest when massive objects are moving very fast. That occurs just before the neutron stars collide. Then the collision occurs and the light is emitted. Qualitatively, at least, that tiny delay is expected. So there you have it. Using what is called multi-messenger astronomy, which is when researchers combine information from different kinds of detectors, we now have a very precise measurement of the speed of gravity. Einstein's conjecture back at the beginning of the 20th century was true. Okay, the fact that the speed of gravity is the same as the speed of light was something that made a lot of theoretical sense. But I'm personally much happier when you can make a direct measurement. If you enjoy learning about all of this cool physics stuff, please like the videos and just poke that button down there to subscribe to the channel.